All right, so some properties of definite integrals we've talked about already, and some of them we have not. So these first two properties right here, okay, if we have a function f defined at x equals a, where these two lower and upper limits here are the same, a and a are the same, so if I integrate something at the same point, am I going to have any area underneath it? No, so the area is going to be 0 for that. So if you have anything that's integrated from the same bounds, it's going to give us 0. And then we've also talked about this one. If we have the integral from b to a, but then I switch that order of it, I'm going to have to make it a negative in order to change it from a to b. So in order to change how those lower and upper bounds go, we do have to make it a negative. The additive property says, I'm going to draw yourself a little picture here. If I had a little graph, and this was point A, and this was point B, okay? Let's say I had some graph, I don't know, could look like this, and like that. Okay, if that was my graph, and I was integrating from A to B, that means I would be finding the area underneath that curve of that function, okay? But we could also break this up and say, okay, well, what if I had a point C in here? Let's say that this was point C at the origin. Do you guys agree that I could take from A to C the area underneath that curve and then add that with the area from C to B, and that would be the exact same thing from A to B? Yeah, it's just a different way of writing it, okay? And then these next three underneath, if we are given the integral from a to b of k, where k is a constant, then I can just think about moving that k on the outside and then integrating it with my function and just getting that as an answer. Number 5, if I have a constant, if we had k was like 5, okay, then this would be 5 times whatever my upper bound minus my lower bound is for my integral. And lastly, number 6 here. 6, we've got two functions, f of x and g of x. And if I integrate both of those individually, I can integrate a to b of f of x, and then I can add or subtract a to b of g of x, okay? So I've got two different functions I can integrate, and then I can add those things together, okay? Add or subtract. So let's use these 4 properties down below to answer these like 6, I think there's 6 questions here, okay? So for the property, or for this set of 6 questions here, we're given from a to b of f of x is equal to 8. We're given that a to b of g of x is equal to negative 3. And then we're given that from a to b of h of x, we're given 5/2. So we're going to kind of use those 3 things and then plug those values into our function that we're given using our properties, okay? So if I look at example A goes from A to B, or sorry, from B to A of g of x. Now that's using that middle function here, right? However, what's different between how those are written? The B and the A are flipped, right? So if I want to flip those, I'm going to need to make this negative. So this is now going to become negative integral from A to B of g of x dx. And I already know that g of x dx is equal to negative 3. So I can just plug that in. This is going to become negative 3, which is just positive 3. Okay, letter B, I'm going from a to b of 2 times my function f of x dx. Well, I could rewrite this as 2 times the integral a to b of f of x dx. And I know that a to b of f of x dx is equal to what? 8, right? So then I can just go ahead and plug in 8 where I see that function, and I end up with 16. Okay, example C, we're integrating from a to b of a number. Now, are we given just a number up here in these properties? No, but if I look up above, property number 5 tells me that if I just have a constant, when I integrate that, it's that constant times b minus a. So I can just plug in 5 times b minus a.
I have come filled with a K, famously.
Yes. Okay. Letter D I can split up. This is the same thing as the integral of a to b of 5 dx plus the integral of a to b of g of x dx. Well, we know g of x dx from a to b is equal to what? Negative 3 from up above. And then we also know, we just found actually what the integral from a to b of 5 is. We just found that to be 5 times b minus a. So I can just plug that information in. So this is now going to become 5 times b minus a, and then minus 3. Yeah, we could simplify, distribute, but we can just leave this as our answer. Okay, letter E I'm going to subtract. So I'm given the integral from a to b of f of x dx. And I'm going to subtract the integral from a to b of h of x. Now we know from a to b of f of x is equal to 8. And then we know the integral from a to b of h of x is going to equal what? 5 halves. Okay, so I can evaluate this by plugging that in. So I've got 8 minus 5 halves, which would be the same thing as if I made this into a common denominator. It would be 16 over 2 minus 5 over 2. So that would equal 11 halves, or 5.5. Yeah. Okay, and this last one, f, I'm going from a to 4 of this function h of x, and then I'm going from 4 to b of h of x. So what am I going to do for this one? Yeah, if I go back up here and look at this property, right, with this picture that I showed you, if I have that upper bound and the lower bound are the same, I can rewrite that integral just to be from a to b. So I can rewrite this integral for letter f to be from a, because 4 is the same as 4 here, so from a to b of h of x dx, that's going to equal what? 5 halves. We just had to use that property so that we could rewrite it and then evaluate it. Okay, what questions do we have on these 6 examples? Do we feel okay about it? Okay, moving on to the next page. Okay, now for this problem we're going to kind of use algebra in order to solve a piece of calculus. Okay, so I'm trying to solve from 1 to 5 of the integral f of x dx. But I'm given this equation right here is equal to 34. So using our properties of integrals, we can rewrite it and then we can solve for that piece. Okay? So I'm going to start out by rewriting it in terms of splitting up where that plus sign is. Okay, so I can rewrite this as the integral from 1 to 5 of 3 times f of x dx plus the integral from 1 to 5 of 4 dx is equal to 34. Okay. Well, what property can I use to simplify this first one? To make it look just like this. Take the 3 out. Okay, so I can take the 3 out in front. And then I have the integral from 1 to 5 of f of x dx. So now this piece is by itself. We can solve for that piece. Obviously, we'll have to get rid of the 3, but we'll do that here in a minute. What can I do with this second piece here? If I've got from 1 to 5 of 4, what property can I use from the previous page? If I just have a constant. Yeah, it's 4 times b minus a. In this case, is 5 minus 1. Is equal to 34. Now we just got to do a little bit of algebra. What is 4 times 5 minus 1? 16. So if I rewrote this, this is 3 times the integral of 1 to 5 of f of x dx And then if I subtract that 16 over 34 minus 16, that's going to give me 18. And now how am I going to get that integral piece by itself? Divide by 3 on both sides. So the integral of 1 to 5 of f of x dx is equal to 6. Okay. Now, for this next question, we have to remember some things about a graph. If I asked you what an even and an odd function looked like, what would you tell me for an even function? What does an even function look like? That means like x to the second power, or x to the fourth power, or negative x to the sixth power. What's my end behavior of those graphs going to look like? For x squared, x to the fourth, they're always going to either be up, or if it was negative, they're going to be down, right? So they're always going to be the same. So if I were to ask you the question of, well, from 0 to 3 of my graph underneath the area, that's equal to 8, what would the area be from negative 3 to 3? Well, if I have my graph, let's say my graph looked something like this. It was just an x squared function. And if I looked at from 0 to 3, the area underneath that curve is going to equal 8. But what if I look at from negative 3 to 3? What's the area underneath the curve over here? Well, yeah, the area on the left side, though, is also 8, right? So then together, the area would be 16. Okay, so if you're told that it's an even function, we can use that idea of it being symmetrical across that y-axis in order to evaluate the area underneath that curve. Okay, if it was an odd function like x cubed, looks something like this, goes up to the right, down to the left, or if it was negative, it would go vice versa, right? And if you were told that from 0 to 3, the area underneath the curve is 8, what would we say from negative 3 to 3? Well, on the other side, what's the area going to be down below the x-axis? It's going to be negative 8, right? So negative 8 plus 8 is going to give me 0. Okay, these last I'm just going to kind of talk through. We're not actually going to do them because we've already done similar ones to this on a previous set of notes. But if you are, it says to sketch this region and then evaluate using your geometry formulas. If I were to sketch x plus 3, what does that look like? It's a line, right? So I'm going to have some sort of line, and then I'm going to evaluate from 1 to 4 on the graph. So what shape is that going to make there?
Triangle?
Trapezoid, yep. So I could split it up into a triangle and a rectangle if I wanted to, but then we could find the area of that function. Okay, but we're not going to because we've done that before. If I look at b, anyone remember what b looks like on a graph? Square root of 4 minus x squared.
It doesn't go into the negative.
It doesn't go into the negative, right? But if I rewrote it like this, what does that look like? That's a circle. So just like what Jacob said, it's actually just going to be the top half of the circle. Okay, so from negative 2 to 2, we've got this semicircle. So I could find the area. I could find the area underneath the curve right here. Okay? And that would be evaluating it using geometry. Okay, first question is, suppose we want to find big F of x whose derivative is little f of f equals 3x squared. What would it be? So what could I take the derivative of and get 3x squared? X to the third, right? If big F of x, ooh, that was very large. If big F of x was equal to x to the third power, and I took the derivative of it, then I would get 3x to the second power. Now, is that the only thing that's going to give me a derivative of 3x to the second power? No, it's not. I could add a number to this. If I added any number, like if I added 7, what's the derivative of 7? 0. So is it going to change that derivative of 3x squared? No. So I could have any number added to this x to the third power to give me the derivative 3x squared. Okay, so there are, in fact, many, if you look down below here. And the way that we're going to write this is by using a plus c. Okay, that plus c is what we call the constant of integration. Okay, it is just a number. It is not a variable. It is standing for a number. Okay, so when we take the integral of little f of x, we get big F of x plus c. Okay, we have to write plus c because we're not given any sort of bounds for what my integral is that we're evaluating. Okay, at the end of class today, we will talk about when we are given bounds, we don't need that plus c, but we need the plus c if it's just an integral that I'm evaluating not at a certain point. Okay, so we've got 6 basic rules here. We've talked about some of them already, but I'm going to kind of give you an example of what they mean. So like if I took the integral of 0, that's going to give me a number. So if I think about this vice versa, if I took the derivative, let's say, of 7, what's the derivative of 7? 0. Remember, they're inverses of each other. So if I take the derivative of a number, then I'm going to get 0. If I take the integral of 0, I get a number. Okay. Similarly, number 2, if I have a constant, that's k, my integral is k times x. So if I took the derivative, let's say, of 7x, the derivative of 7x gives me 7. So the derivative of k times x gives you k. They're inverses of each other. Okay, 3, 4, and 5 we talked about on the previous slides, where if it's a constant, we can take that constant here outside of my integral to now have the constant times the integral of f of x. Number 4 and 5 just say that we can add and subtract those functions separately because it will be easier sometimes to split them up, actually almost always. And then number 6 is going to be the one that we spend most time with today. If I have an integral of some variable x to some number n power, this is our formula. So let's say I had the integral of x to the 7th power. Okay, if I evaluate this, I'm going to plug in 7 where I see an n. Okay, so I'm going to keep the x. This is going to become 7, excuse me, plus 1 divided by 7 plus 1. Plus c, don't forget the plus c. People always forget the plus c. Don't forget it. And then we can simplify this. This is actually just x to the 8th power divided by 8 plus c. Now, if I took the derivative of this, take the derivative of x to the 8th divided by 8. I would get 8 divided by 8 times x to the 7th power, right? Which is exactly what we started with. Okay, they're inverses of each other. Okay, so we're going to use this formula to evaluate some antiderivatives. Okay, when I say antiderivative, when I say integral, those things all mean the same thing. So looking at the first example here, I've got the integral of 3x dx. So I can think about this as the same thing as the integral, as 3 times the integral of x dx. X is technically to what power there? 1. So if I use that property 6 of above, my 3 is just going to stay there with my answer. So I've got 3 times x to the n plus 1, or x to the 2nd power, divided by 2. But what am I forgetting? Plus c. Okay, so your answer, we can combine that fraction together. So 3x squared divided by 2 plus c. Either one of those answers is fine with me. But questions on that one? Double check your work. If I took the derivative of this, what am I going to get? 6x divided by 2, which is 3x, which is where we started with. Okay? All right. Letter B, I've got 1 divided by x to the 3rd power. Have we talked about any sort of multiplying or dividing things?
No.
No. So I can think about rewriting this. If I wanted to rewrite this 1 over x to the third power, how would I do that? X to the negative third power. Okay, now could I use that power rule there to rewrite with my integral? I bet I can. So this is going to become x to the negative 3 plus 1, which is negative 2, divided by also negative 2.
Plus C.
Plus C. Plus C is always where people forget.
Always.
I could split up that fraction to be negative 1/2 x to the negative second plus C, or I could even rewrite it technically as negative 1 over 2x squared plus C. Okay? That is fine, though, how I first wrote it. If you really want to simplify it, you can, but you don't have to. Okay. Moving on. 4 examples, we'll take a break. I think I totally forgot to do example 2 with last class. That's okay. I'll do it with them next time. All right, so example C here. Example C, let's rewrite that in terms of an exponent that we can add 1 to. So this is the same thing as the integral of x to the 1/2 power. So go ahead and take the integral of x to the 1/2 power. Did we all get x to the 3/2 power divided by 3/2 plus c?
Yeah.
Yes? Could I rewrite that so it's not a fraction and a fraction?
1.5?
Yes. I still don't like decimals and fractions. Could I rewrite it as 2/3 x to the 3/2 plus c?
Yeah.
Isn't that the same thing technically as 1 divided by 1 divided by 3/2 is the same as 1 times 2/3 to give me 2/3. Okay. It'll be nicer when you start, because we're going to eventually have to start evaluating these things. So dividing by that 3/2 is going to be harder for our brains to do than multiplying by 2/3 when we can't use a calculator. Okay. So that is our answer for that one. Okay. Letter D. Now again, there's multiplying happening. Have we talked about anything with multiplication and like product rules or anything? No. So what we're going to do is we are going to distribute the cube root of x to both of these things. So in order to do that, let's rewrite x as to the 1/3 power times x minus 4. And now we can distribute. So really, I want us to take the integral of x to the, what is 1/3 plus 1 going to give me? 4/3. And then minus 4x to the 1/3 power. Okay, so yes, we can do exactly that. Now that I have a subtraction sign in between there, we can separate these into the integral of x to the 4/3 minus 4, because I can take that constant out, times by the integral of x to the 1/3 power. And I should always have a dx afterwards, or a d times whatever variable we're using there, in order for that to be a proper integral. Okay. Now we can go ahead and take those integrals. Okay, the integral of x to the 4/3 power, that would be x to the 4/3 plus 1. What's 4/3 plus 1? 7/3. And then I'm dividing by 7/3.
Or 3/7 times x to the 7/3.
Or you can rewrite it, yes, and I'll do that next. And then I'm going to subtract 4 and times it by the integral of x to the 1/3. So x to the 1/3 plus 1, x to the 4/3. And I'm going to divide that by also 4/3. Plus c. But let's rewrite that so we don't have fractions and fractions. So my final answer would be 7/3 on the bottom becomes 3/7 as a reciprocal. So 3/7 x to the 7/3 minus 4 times 3/4 x to the 4/3 plus c. And then could I do one more simplifying there?
Yeah.
Yes, those 4's could cancel out. So our final answer, 3/7 x to the 7/3 minus x to the 4/3 plus c. Oops. My bad, there should be a 3 right there. There we go. All right, we got to do some algebra here. We got fractions. Everyone loves fractions. Let's rewrite this similar to how we just did letter D. Do you guys agree that I could rewrite this as x to the negative 1/2 times x plus 1. Is that the same thing? Yeah. And now from here, could I distribute so that way I can actually integrate this? You bet I can. So this is going to become the integral of x to the negative 1/2 plus 1 is going to be 1/2. And then plus x to the negative 1/2 dx. So I can integrate both of these things individually. So this would be the integral of x to the 1/2 dx plus the integral of x to the negative 1/2 dx. Now, you don't have to necessarily show this step of going from this to the separate integrals. If you want to just go straight to integrating each of these pieces individually, that's fine, okay? And that's eventually what you'll probably start doing. But I just want to show you how they're getting from one to the other for here. So integral of x to the 1/2, that's going to become x to the 1/2 plus 1 power, which would be 3/2 divided by 3/2 plus the integral of x to the negative 1/2 would be x to the positive 1/2 divided by 1/2 plus c. And then we can simplify this a little bit nicer so that way we don't have fractions and fractions. So this is actually 2/3 x to the 3/2 plus 2 x to the 1/2 plus c. I always almost forget the plus c. Okay. All right, integral of t squared plus 1 to the second power. What are we going to do? Algebra. Yeah, let's distribute this out, right? So this is actually going to become the integral of t to the 4th power plus 2t to the 2nd power plus 1 dt. Yes? Okay, now from here we can use that rule to evaluate each of these integrals separately and add them all together. Okay, so I'm going to give you guys a minute, evaluate each of this individually, and then don't forget your plus c at the end, and I will go over the answer here in a minute. All right, did we get t to the 5th power divided by 5 plus 2t to the 3rd power divided by 2, divided by 3, and then plus t plus c. We all get that? If we integrate just a number, remember, it's that number times your variable t, okay, or your variable x, whatever your variable is. Because if I took the derivative of t, that's going to give me what? 1, okay? The derivative of 2t to the 3rd would give me 2t squared. Derivative of t to the 5th would give me t to the 4th, okay? All right, we will take a quick little break here, and then we'll come back together and do some more. Okay, so we're given a bunch of things. We're given second derivative is 3, first derivative is 5, and then f of 2 is 10. Okay, we're going to find f of x. Well, if we think, okay, if I write... Oh, sorry, yes, you're right. If I wrote this as f prime of x, f prime of x is technically the integral of the second derivative. If I took and put this as the second derivative here, those are inverses of each other, okay? If I took the integral of the second derivative, I end up with the first derivative. If I take the integral of the first derivative, I end up with just the function f of x. So I know that the integral of, that the f double prime of x is equal to 3. So I can plug that in. So as the integral of 3 dx, and I can evaluate that. The integral of 3 is just 3 times what? X. So this is actually equal to 3x plus c. Okay, so now I know that f prime of 2 is equal to 5. So this function, f prime of x, is currently equal to 3x plus c. But if I plug in 2, right? Then I can actually solve for what c is equal to. So I'm going to write f prime of 2 is equal to 3 times 2 plus c. And what does f prime of 2 equal? 5. So this is 5 equals 6 plus c, which means that c equals -1. Okay, so my f prime of x function is actually 3x minus 1. Okay, but I want to find f of x, and I have f prime of x. So if I want to find f of x, I can take the integral of f prime of x to get f of x. So let's rewrite this on the side here. The integral of f prime of x dx is equal to the integral of 3x minus 1 dx. Okay, well, we can evaluate that. The integral of 3x minus 1. If I integrate that, I would have 3x to the second divided by 2 minus x, but plus c. Okay, so this right here, when I integrate f prime of x, this is actually equal to f of x. And now I have some information that I've been given. I've been given that f of 2 is equal to 10. So can I plug in 2 for x? Yeah. Okay, so let's plug in 2. So I get 3 times 2 squared divided by 2 minus 2 plus c is equal to f of 2, and f of 2 is 10. Okay, so if I simplify this, I'm going to be able to solve for c. Okay, so this is 3 times 4 divided by 2, so that gives me 6 minus 2 plus c equals 10. So that means 4 plus c equals 10. So what is c going to equal? 6. Okay, and so we were given a function, f of x here, but the only thing that I did not know was what c was equal to, right? So now that I know what c is equal to, can I plug that in? Yes. So if I plug that in, my f of x function is equal to 3x squared divided by 2 minus x plus 6. This next rest of this page is just some things that we eventually will need to have memorized, okay? But in the meantime, we're just going to write them down. So we're going to think to ourselves, what can I take the derivative of to get cosine of x? Sine. So the integral of cosine of x dx is equal to sine of x plus c. What can I take the derivative of to give me sine? Negative cosine. So negative cosine of x plus c. Let's work our way down the second column there. What gives me the derivative equal to secant squared of x? Tangent of x plus c. What can I take the derivative of to get secant x tangent x? Secant x, yes, plus c. Okay, moving our way back to cosecant. What can I take the derivative of to get cosecant squared? Cotangent, but make it negative, actually. So negative cotangent squared of x plus c, if I take the derivative of it, will give me cosecant squared. And then what can I take the derivative of to give me cosecant cotangent? Cosecant, but make it negative. If I take the derivative of cosecant squared x, technically I get negative, right? Cosecant x, cotangent x, but I want positive, so we got to make it negative. Okay, so these two over here are tricky. They really are. Okay? That should not be squared. Sorry, guys. Just negative cosecant of x. And both of them. Why did I put both of them as squared? I don't know. Sorry. Pause, my bad. Okay. Are we good now? Okay. And then, oops, the integral of log functions. The nice thing about e to the x is it's always going to stay consistent. E to the x is e to the x is e to the x. Okay? The only thing that's going to be different is that you have to add a constant plus c with that. Next thing, integration with bases that are not e. If it was like 5 to the x power, okay, then you're going to use this formula of 1 over the natural log of the base times that function, a to the x, and then plus c. So we're going to use these two here to do an example of those two kinds, and then we got just the rest of that page, and then we'll be done. Okay? All right. So we're using that first rule on the back of that page on the bottom. If I integrate 5e to the x, I'm just going to be left with 5e to the x plus c. Six to the x is not a base of e, but when I take the integral of this, it's just going to be 1 over the natural log of 6 times 6 to the x plus c. Last formula here that we'll talk about today and we'll get practice with again next class. If I have the integral of 1 over x, the integral of 1 over x is the natural log of the absolute value of x plus c. So if I have 5 divided by x dx and I'm taking the integral of that, my answer would just be 5 times the natural log of absolute value of x plus c. Now if I wrote the answer like this, are those two things the same?
No.
They are actually. Using log properties, I can rewrite exponents by moving them down in front of the log. Okay, so technically those are the same thing, but rewritten using log properties. So that could be like a multiple choice kind of question where you get this answer, but this is actually the only answer that's on there. So use those kind of ideas. All right, now we're going to use the fundamental theorem again. However, this time is how it's going to be most commonly used throughout the rest of the semester. Is we are going to evaluate these integrals at certain points, okay? So we do not need any plus c's here anymore, and I will show you why that is, okay? So I'm going to do a little mini proof over here on the side. You don't have to write this down. If you want to, you can. But if I was looking at the integral from -2 to 4 of x, okay? If we integrate x, when I integrate x, I get x squared over 2. Do we agree? X squared over 2, technically plus c. If it was not any bounds, yes? Okay, but then these bounds, these upper and lower limits here, what that means is I'm going to evaluate it at both 4 and -2. So that like long bar kind of just means I'm going to put in 4 and -2, and I'm going to subtract those two things from each other. Based on our fundamental theorem of calculus, okay, I'm going to take f of b, capital F of b, means I'm going to integrate this and then plug in b, and then I'm going to subtract the integral of f, lowercase f of x, and then plug in a. So if I do that here, I'm going to plug in 4 where I see x. So I get 4 squared over 2 plus c, and then I'm going to subtract the quantity when I plug in a -2. So -2 squared over 2 plus c. And now if I evaluate this, 4 squared, 16, divided by 2 is 8. Minus, let's see, what is that? 2 plus c. But these parentheses means I've got to distribute that negative, right? So then technically I've got an 8 plus c minus 2 minus c. So do we see where those c's go? Knee slapper there. Okay, so I get what? 6. Okay? So if you also plug this into the calculator, you guys remember how to plug in the integrals on your calculator, that button, you'll get 6 as an answer, okay? But you're going to have to show your work on these problems, especially when there is no calculator portion, right? These are questions that we can do without a calculator with no problem, so you will have to be able to show your work. Okay, so we do not need to write a plus c whenever there is numbers on the lower and the upper bounds. So if I look at letter A, we're looking at from -2 to 4 of 10. So let's integrate 10. If I integrate 10, what do I get? 10x. So 10x, and I'm evaluating that at 4 and at -2. So that means I'm going to plug in 4, and then I'm going to subtract what I get when I plug in -2. So I've got 10 times 4 minus 10 times -2. So that means I get 40 minus a -20, which gives me 60. Okay, please, please, please show your work. So that way if you make a silly mistake somewhere, I can give you partial credit. We're going to go down the left-hand side here, and then we'll go over to the right. Okay, I've got from -pi/4 to pi/4 of 2 secant squared theta d theta. Okay? So we got to think, what is the integral of secant squared theta? What can I take the derivative of to get secant squared of theta? Tangent. So the integral of this is going to be 2 times tangent of theta. And I'm going to evaluate this at pi/4 and at -pi/4. So I've got 2 tangent of pi/4, and I'm subtracting 2 tangent of -pi/4. And again, this should be one that we should do without a calculator, or can do without a calculator. Tangent of pi/4 is going to be what? 1. So I've got 2 times 1 minus 2 times, how's the next one going to change? -1. So evaluate that. I get 2 minus -2, which is positive 4. All right, looking at letter E. Letter E, we are going from 0 to natural log of 5 of e to the x dx. So the integral of e to the x is e to the x. And we're evaluating it at natural log of 5 and at 0. So I'm going to plug that stuff in. E to the natural log of 5 minus e to the 0. Well, what does e to the natural log of 5 actually give me? 5. Those go away. I'm left with 5. So I have 5 minus e to the 0, which is 1. So this equals 4. Do you guys remember what natural log of 1 equals? 0. Yeah, nice. Oh, that reminds me. There will be on your homework, I'm going to write it down right here, this trig identity that will help you simplify some of your problems. Sine squared plus cosine squared equals 1. Hopefully you remember that one. Yeah. So you might see that on your homework. If you're not really sure what to do and you see both trig functions there, you could probably just replace that with 1. They mean the same thing. Okay? Alrighty. Moving on back to letter B. We've got x squared plus the square root of x. So I'm going to think about this one as x to the 1/2, but I'm not going to rewrite it completely. So I'm going to integrate x squared. If I integrate x squared, what do I get? X cubed over 3. So I add 1 and then divide by that same number.
Wait, why is it over 3?
Because, so I add 1 to the exponent here for x squared, and then I divide by that one as well. Yep. And then x to the 1/2, if I add 1 to that, I get x to the 3/2, and I divide by 3/2, which can I also just write as 2/3? Yeah, that'll be easier to evaluate. So now I can evaluate this at both 1 and at 0. So when I plug in 1, I get 1/3 plus 2/3, right? When I plug in 1. And then I've got to subtract what I get when I plug in 0, which is just going to be 0, right? So that's not going to matter there. So my answer when I add those things together is going to give me 3/3 or 1. Okay, let's look at letter F and then we'll come back to letter D. Letter F is just a little easier. Okay, I've got 3 over x. So if you look just above, when I have 1 over x, that's going to give me the natural log of absolute value of x. So when I evaluate this, I will have 3 times the natural log of x. And then I'm going to evaluate this at both e squared and at 1. Okay, so when I plug in e squared, I'm going to get 3 times the natural log of e squared. And then I'm going to subtract when I plug in 1. So I've got minus 3 times the natural log of 1. And I mentioned this earlier, natural log of 1 is 0, so this whole thing is going to be 0. But then, can I simplify this natural log of e to the second? I can actually. Natural log of e is just 1. So it's going to be 3 times 2, which gives me 6. One last example. You guys are doing great today. All right, last example, letter D. I've got 1 minus the square root of t over the square root of t. I'm going to rewrite this as t to the negative 1/2 times 1 minus t to the 1/2. Are we okay with how I did that? So the square root of t in the denominator would be t to the negative 1/2. And then I just rewrote the square root again as t to the 1/2. Because now I can go ahead and distribute this so that I can actually evaluate it. Okay, so if I distribute this from 4 to 9, I'm going to have t to the negative 1/2 minus, well, t to the negative 1/2 times t to the 1/2. That's going to give me t to what power?
0.
0. So minus t to the 0, which is actually just what? 1. So minus 1, and then dt. And now we can go ahead and take the integral of that. Okay, so the integral of t to the negative 1/2 is going to be t to the negative 1/2 plus 1, which is 1/2. And I'm going to divide by 1/2, which is the same thing as multiplying by 2.
So 2t to the 1/2.
Yes, but then I also have to evaluate what's the integral of negative 1. Negative t, so just minus t. And then from here we can evaluate this both at 9 and at 4. Okay, so when I plug in 9, I get 2 times 9 to the 1/2 power minus 9. And then if I evaluate it at 4, I'm subtracting this entire quantity of 2 times 4 to the 1/2 minus 4. Okay, always show your work if possible there. So if I evaluate that first piece, I'm going to get 2 times, what is 9 to the 1/2 power? 3 minus 9. And then what's going to happen in this red stuff here? It's all go to 0, right? So then I've got 6 minus 9, which gives me negative 3. Very final answer. Okay, we did a lot of calculus today. Okay, we will practice more on Thursday. Your homework is posted, but it's not due until the next class on Monday. Okay, let me know if you guys have any questions.